So welcome everyone to the second part of our Minisymposium. We're going to have three talks by Jonathan Weare, Pedram Hazanzadeh, and Vasily Kitsius. As before, we have 30-minute slots. I would ask our speakers to please try to stay within that limit, and keeping in mind, to leave some time for Q&A. I'll try to send you a personal message on chat, when you are in the in the 20-minute point in the slot. I'd also like to thank once again the organizers, Georg and Jessica, for putting together this very nice event, and SIAM, of course. I would again ask people to stay muted while the speakers are giving their talk, just to maintain audio quality, and afterwards feel free to either submit questions in the Q&A in the chat, or there should be a raise hand feature somewhere. If you click on participants, I believe there should be a raise hand option, or you can just speak up with your questions at the end. So without further ado, I'd like to introduce Jonathan Weare from Courant Institute, who will be talking to us about characterizing long timescale phenomena with trajectory data.
So thank you, organizers, for inviting me. I'm going to talk today. So there's a long cast of people involved, as you can see. Most of what I'm going to tell you about today, the examples are going to be drawn from computational statistical mechanics, from biophysics in particular. So I know that's well, depending on how you look at it, may or may not be mathematics of planet Earth. The ideas are pretty general, and in fact we have an effort applying some of these same ideas to geophysical flows, but I have more well-developed examples for these biophysics problems. So I'm gonna...
Just a quick interruption. We don't see the full full screen version of your talk. I don't know if that was intentional. Like we're
you
seeing,
don't.
we
So
see
you see like all the stuff on the side?
Yes.
Huh. In fact, let's see. So if I go, so now you see not a full screen version, I guess.
No.
And now this doesn't change anything.
Nope.
Okay.
Maybe in view options, you have to go to view options. And
well, I opened on my computer. It is showing full screen, but maybe.
I think you know what you could try maybe.
I'm in Acrobat. Maybe I should just use preview. Should I try that?
Preview works for me.
Okay.
And I just shared the window. I just shared the window of the PDF on Zoom. I don't go full screen.
Okay, let me try that.
But preview tends to have less clutter, I guess. So it's almost like.
So I shared Acrobat. Should I just share my desktop, or?
You could try.
You know what? Let me try
preview
and just see if it works better. Sorry about that.
It's not your fault.
Well, that's what it is. Oh. I can't remember how I did this last time. Everything worked fine.
So if you open the PDF on preview and you do share screen, and it gives you, you should see like a list of windows, right?
Yeah, and then I'm choosing the preview window.
And then you click share and nothing happened.
Well, that's what I did for, let's see, that's what I did for Adobe, but it didn't seem to work, but maybe it'll work for...
Now we can see your preview. Oh, yeah, there you go. No, yeah,
okay,
yeah.
Good. Sorry about that. Okay, so let's see, let me just run through them. So Aaron is a longtime collaborator in chemistry. Douglas was an undergrad at U Chicago who is going to be a PhD student at Courant. Justin is a PhD student at Chicago, but working with me. He's the one that's really in charge of applying the ideas that I'll talk about at the end to geophysical flows. I think you guys know the next person. He was involved in, Dimitris was involved in the second part of the talk, and I don't know how much of that I'm going to get to, but John and Eric are grad students in chemistry. Eric actually just graduated, working on applying these things to biophysics problems. And Rob is an applied math student who will graduate this year. He's worked on a lot of the analysis. Okay, so all right, I'm going to go fast through these things in the beginning because I've already burned a lot of my time. The most interesting events often occur very infrequently. I don't know how much convincing you need of that, but infrequent may depend on, for example, the time scale of integration. So hurricanes, well, they happen infrequently if you're thinking about the time scale of a single time step. Same with major blackouts, same with the major conformational changes responsible for the behavior of therapeutics. Okay, so you got to reach these very long timescales to interrogate the process. You have a few options. One is to build a really fast computer. So Anton is a computer specifically meant for molecular dynamics simulations. You can reach certainly reach longer timescales with that. The other is coarse graining or model reduction. So there's certainly a lot of work on that, building approximate models for a subset of the variables in the system. Okay, and another one that we've worked on a lot is rare event simulation, which is trying to somehow bypass the time you have to wait for the model to undergo the event you're actually interested in. So you're not really interested in the little jigglings that it does on a very short time scale. You're interested in some behavior over a very long time scale, and rare event simulation tries to simulate those events more directly. Okay, however you've generated your data. So let's assume that by one of those methods, you've generated a bunch of data, and your goal is to understand some rare event. You need to somehow process that data, that trajectory data. So in all cases, I'm talking about trajectory data. So I have many short trajectories where the trajectories are just generated by running the model forward. It may be, and in fact, in the cases that I'm interested in, it will be that none of the trajectories are actually long enough to see the event you're interested in. So somehow from many short trajectories, you want to learn something about long time scale phenomena, about these rare events. Okay, so I'm going to talk about two approaches to that kind of question. The first one we have nothing to do with introducing. So people on this meeting, in this call, have contributed to the methodology here. But also a lot of work was done in molecular dynamics, and we're going to focus a little bit on that, more on the assumptions for that setting. But what we're going to do is try and provide an analysis of these well-established schemes. I'll describe them in a second. Some of you will be familiar with them. They're essentially attempts to estimate the eigenvectors and eigenvalues of a transition operator or a Koopman operator from trajectory data. Okay, so that's more of an analysis thrust, a numerical analysis thrust. The part two is really within the same circle of ideas, but a different set of methods. So in part two, we're really saying, look, suppose you have a specific rare event in mind and a specific statistic. I'll talk about the kind of statistics you might want to compute. Using the same kind of technology, you can bypass computing eigenvalues, eigenvectors, and just compute the statistics you're interested in. Okay, so the first thing I'm going to talk about it's a pretty broad family of methods. We're going to go by the name that it goes by in molecular dynamics, which is the variational approach to conformal dynamics. The only word that is really useful there for us is the variational. And I'll explain that in a second. Okay, so the idea, so there's this in the box, this transition operator. So this operator computes the you supply a function f that you're interested in, and it computes or gives you back, if you could apply it, the expectation of that function at a future time as a function of the current state. So this might be some function of the weather in the future given the current weather as described by whatever model you're using. Okay, and you'll notice this this tau. Can you see my cursor here, or is that just for me? Can you see my mouse?
Yes. Yes.
Okay, so you'll see this parameter tau. That's called that's usually called a time lag or a lag time. Goes by both. So that's going to be an important parameter. We're going to focus a bit on how on the properties, the error properties of this algorithm as you change that parameter. It's been talked about a lot in the literature by trial and error, because it has a pretty big effect on your accuracy. Okay, so what are the assumptions here? XT it's assumed to be an ergodic stochastic dynamical system. So it has some invariant measure mu, some ergodic measure mu. The biggest assumption that I'm making from the point of view of someone that is interested in geophysical flows would be self-adjoint. So so I am going to, because it's appropriate for these molecular dynamics problems, I'm going to assume that and because the analysis will depend on it, I'm going to assume that the transition operator is self-adjoint. I don't think that that has a huge effect on some of our conclusions, but it certainly has an effect on the techniques. I'm also going to assume that the operator is what's called quasi-compact. So it has an eigenvalue, the transition operator has an eigenvalue of 1. It has a unique ergodic measure, so if it's quasi-compact, that means that the rest of the eigenvalues are smaller than 1. And then, so, I mean, you can, if this was compact, if this was a compact operator, there just wouldn't be an R here. This would be like a singular value decomposition. It's reversible, so it's really an eigenvector decomposition of the transition operator. Okay, so the notation is going to be a little bit important. As I said, these e to the minus sigma tau, these are my eigenvalues of the transition operator. You can see they depend on tau in a very predictable way. They're ordered so that higher indices, higher R's, mean that the eigenvalue is smaller. And they're associated with eigenvectors, eta 1 through eta R. Okay, and the first one is the constant function. So the constant function is always, because probability is preserved, the constant function is always an eigenvector. Okay, so that's the notational setup. And the goal of VAC is to really approximate these eigenfunctions. So, or maybe more specifically, the span of some set of eigenfunctions of the transition operator. So why would you want to do that? Well, again, in the reversible case, you have some easy calculations show you that these eigenfunctions really describe what's a quickly decaying, what's a quickly decorrelating function versus a slowly decorrelating function. So the eta with low index are going to be slowly decorrelating. So if I tell you the value of eta in the beginning, the value of eta in quite a lot of time is going to be close. Isn't going to change that much. Whereas for high values, for high indices, high indice eigenvectors, they decorrelate very quickly. Okay, So, so the idea here with VAC, is that these slowly decorrelating functions can be used to describe rare events. So you have to hope a little bit that the rare event that you're interested in corresponds to these slow eigenfunctions. And I'll discuss later, you know, in fact, for complex systems, that's often not the case, but it is the case. It is the case up to the resolution of your data in many cases. So, so there's a bit of a loose connection between the rare event of interest, if you have a specific one in mind, and these slowly decorrelating eigenfunctions. But it is often an effective way to go. So you can see here, this is actually a very simple model of sudden stratospheric warming. So I said I was going to focus on molecular dynamics examples. This is the only atmospheric dynamics example, but and it's a very simple model. But you can see here we've identified so again, the first eigenvector is just the constant. That one's not so interesting. Here we've identified the second eigenvector, and we're looking at its value as we evolve the time series forward. Look at the value of the function at the state as you increase time, and you see that it has this metastable property. That variable, that slowest eigenfunction, tends to hang around, be about 20 for a long time, and then makes a sudden switch to being around 0, and then switching back. Okay, so it's describing some slow process. It's slowly decorrelating compared to the time scale of these wiggles that you see between transitions. Okay, so let me just describe the basic workflow. It's a fairly simple algorithm. Step one is to generate, so I remember that mu is the invariant distribution. So I'm going to describe a simple version of this scheme where you actually generate the samples from mu from the stationary distribution. So for example, by running a very long trajectory, which I said I generally want to avoid, but there are ways around that. I'm just going to keep it simple and assume that you have generated your initial conditions from the stationary distribution, and then you evolve each of those initial conditions forward in time by just pushing the button on the dynamics to generate a sample of x tau for every x0 for every copy of the initial condition you have. You have to have selected a set of basis functions. This is going to be a method that uses a basis expansion of the eigenfunctions. So you select a set of, often they're called features, and then you want to approximate both the covariance of the basis functions and this c tau, so time lag covariance, autocovariance. And then you solve for the eigenpairs of C0 inverse c tau. This is just a very standard, so if it doesn't make, if it's not immediately clear, and it's probably not, why this works, that's fine. This is just the completely standard way to discretize this eigenproblem and try to solve it. So project the solution onto this basis set. So if I do this with the C matrix, C0 and C tau, then there'll be no sampling error. C hat indicates some sampling error. So hats in general in this talk are going to indicate some sampling error. So there's several errors. There's first the error from the fact that these basis functions may not be able to perfectly represent the eigenfunctions. And there's error from the fact, so if they were able to perfectly represent the eigenfunctions, then by solving for the eigenpairs of C0 inverse C tau, I would have no error. But I have both the basis function error, which we call approximation error, and I have error from the fact that even if I had the perfect basis, I cannot compute C exactly. I have to do it by sampling. Okay, the eventual approximations of the eigenfunctions are these gamma hat functions. They're linear combinations of the basis functions. Okay, so the most common variants in molecular dynamics are Markov state models. So what that corresponds to is a very specific choice of basis functions. They're, you chop up space. Often some attempt is made to chop up space and to partition space in a clever way. And then once you partition space, you define the functions that are 1 on each partition and 0 off the partition. So we would call that a basis of indicator functions. And then there's another scheme called TICA, in which the basis functions are actually just the coordinates themselves. So those are kind of two extremes. Sometimes they're mixed in various ways. Okay, so that's the basic VAC workflow. So just an example, this is somebody else's SIDKey, somebody else's application of the VAC to the folding of a mini protein called trip cage. It's, so this would be, I think this is about 30,000 dimensions. It's 11,000 atoms. That includes solvent and this mini protein. And what we're interested in is how it goes from unfolded to folded. Okay, so they've done TICA here, which is why these coordinates are called ticks. And then you'll often see plots like this. So they've solved that eigenproblem in the basis of just the coordinates themselves. In fact, they probably use internal coordinates, but essentially in the basis of the coordinates themselves. And then they plot the eigenfunctions that they find against each other. Okay, and you'll see plots like this. And it looks like this was effective, at least at picking up one metastable transition. Okay, but the obvious question is, when should we trust this approach? I mean, in other words, for a numerical analyst, what's the error? When is the error big? When is the error not so big? So as I said, there's two main types of errors. One is the approximation error. So that just comes from the fact that the basis functions probably don't span the eigenfunctions you're looking for. And so, even if you had no sampling error, there's just a limitation to how well you can represent the eigenfunctions as linear combinations of your basis functions. Okay, and then there's estimation error, which is no matter how good your basis is, you're not using this matrix C, you're using an estimated version of C from Monte Carlo, from sampling. Okay, so we want to understand these two errors. It doesn't matter too much, but there's a particular notion of distance between subspaces. So what we're actually interested in is you give me a set, not just a single eigenfunction, but you give me a collection of eigenfunctions. And again, we're interested in the low-lying, the eigenfunctions with eigenvalues, large eigenvalues. We want to know, so those eigenfunctions would span some space, and our estimated eigenfunctions span a space. We want to know how close are those two spaces. So there's something called a projection distance, which is a nice way to measure the distance between between vector spaces. And you can do that. You can describe it in terms of angles, but I'll leave that. So you'll notice in this first distance for approximation error, there's no hats. So this error has only to do with the fact that the gamma I must lie in the span of the phis. Okay, and in the second one, we have there's a hat here. So this is sampling error, and we're not measuring the distance to the true eigenfunctions or the true eigenspace. We're measuring the distance to the no sampling error eigenspace. So these guys still have approximation error. Okay, but if you put them together, you can get the total error. Okay, so this is an example. The algorithm that I've described is an example of something called the Rayleigh-Ritz. Just checking the time. The Rayleigh-Ritz method, which is a standard method, and there's standard tools of analysis. And in fact, Christoph Schutte and some coworkers used Rayleigh-Ritz bounds to prove prove convergence of the eigenvalues. So that's convergence as the basis set is increased to the point that it spans the space. Okay, so what is left out there is that's for a fixed value of tau. So it doesn't tell you how the error, how that error changes with tau, the error in the eigenvalues. It also doesn't say anything about the eigenvectors, though you can apply standard Rayleigh-Ritz bounds to get convergence of the eigenvectors. In both cases, though, it's not going to give you the right behavior. So here, we're looking at a very simple example, just an OU process, an Ornstein-Uhlenbeck process. So that's a mean reverting version of Brownian motion in 1D. We're using what we call an MSM basis. So that's this indicator. We grid up 1D and use an indicator, a basis of indicator functions. And we just ask, okay, what do the bounds say the error should be, the approximation error? So we're just looking at approximation error now. Well, they predict that there should be a quick fall off in the error as you increase the time lag from 0, but then a quick growth in the error as the time lag increases. And so for this problem, you can actually work out what's the error analytically or exactly. And you find that actually that large tau behavior is quite far off. That actually the error gets better and better and better as you increase the lag time. Okay, so the Rayleigh-Ritz bounds don't do the job. They predict the wrong behavior. So I won't get into the details, but we had to go beyond Rayleigh-Ritz bounds to get bounds that really tell us the correct behavior. And again, it's not just for eigenvalues. This is for the eigenvectors, which are actually the quantities you're more interested in, though you do need to know the eigenvalues too. So rather than go into these details, let me just show you the plots again for this OU process. Again, on the left, the Rayleigh-Ritz bounds blowing up. This is, by the way, this is error on the eigenspace spanned by the first 3 eigenvectors. Okay, this is not eigenvalue error bounds. So you see again that on the left, that's the same plot I had before. The approximation error is blowing up in the bound, but it doesn't actually blow up. That's on the right, the truth. And in the middle is the improved bounds. And what you find is that the approximation error gets better, as I said, not worse, as tau increases. These bounds get that right. Okay, so that was the approximation error. There's also estimation error. And we also provide, we provide an exact expression for that, which you can turn into a bound. But more importantly, you can turn it into a way to compute confidence intervals on your estimates. So what you need is some understanding of the error you make in the C matrix. And from that, you can work out what's the errors you make in the eigenvectors. Okay, so just to show you, put it all together here, this is, I'm showing you again that same one-dimensional OU process. So obviously that's a toy problem. Again, we're analyzing this method, we're not introducing it. The method has been used many times on large problems, including by us. Okay, so what this is showing you is on the left, you have a smaller number of, a larger number of samples and a smaller basis. So if we examine those error bounds carefully, we'd find that increasing the basis without increasing the sampling can lead to larger errors. So on the left, it's a better situation. You have more sampling. So here it's all done with a one long trajectory, more sampling and a smaller basis. And on the right, you see, well, the pictures show you that something bad is happening, and that's a larger basis with a shorter trajectory. Sorry.
John, there are about 5 minutes in your slot. Just mention.
Okay. Okay. So I don't think I'm gonna. Let's see. As tau increases, right? So so the other thing to notice from these pictures is that while the approximation error decreases, so you, from the approximation error point of view, you always want to choose the longest lag time you possibly can. Now, that leads to problems for the estimation error. So in the end, what you have to do is balance estimation error and lag time error. And we've used that to actually introduce some improvements to the method, which I won't get into. I will just very quickly mention this Galerkin approximation scheme, which is designed to compute conditional expectations. So here you have a specific rare event in mind, and we compute conditional expectations involving that rare event. So that's involving Dimitris. I'm not going to try and explain it to you now because it would just be not very pleasant. I'll just show you. You can do some pretty neat things. So here, this is trip cage again. Here, this is a many-dimensional system. I'm showing you a plot in 2 of those dimensions, but it is a many-dimensional system. Everything is done in high dimensions. In this 2-dimensional space, I'm showing you a plot of what's called the reactive current. That's a transition path theory quantity, and it really it's pretty amazing. The level of detail we're getting here. You can see that there's 2. If you follow the arrows from A to B, you can see that there's 2 pathways in this problem, and you can characterize those pathways, including how dominant they are. Okay, and I'll end on this. We're working, as I said, to apply these things on problems that you guys might be more interested in than the molecular dynamics problems. Here's a description really of transition path theory and of some of the quantities we're computing in the context of a low order sudden stratospheric warming model. So that might be helpful. So that does not describe the methods, I should say, but it describes the quantities that we want to compute. All right, so sorry for going too long. I'll stop there.
Thank you very much, Jonathan. Are there any questions? Feel free to speak up. Gary?
Hi, Jonathan. Nice talk. I think these are very natural conclusions with the flow time and the sampling. I just wanted to comment that I think you can probably do pretty much everything you were doing without the reversible dynamics assumption.
I think so too.
You probably know I had a lot of back and forth with Rob Weber by email about this.
Right. Yeah.
So I think that's good news. Or if I mean, maybe your error bounds are much easier to get when you have symmetrized, when you have symmetric operators. It might also be that in many cases you can construct a symmetric operator from a non-symmetric one to solve the problem you want to solve, and then you could apply the bounds to that.
Then you could apply the bounds
that you already have to that symmetric operator.
Right. My guess in terms of the and actually Rob would know in more detail, but my guess is that what changes is really what we have to do to prove things more than the kind of high level conclusions.
Can I ask you a question?
Yes.
Okay. I'm trying to understand the.
That was it though. That was already it.
The VAR slide. So you have the VAR slide. You have that algorithm path, right?
Let me go back. Tell me when.
There was like step 1, you do this. Step 2, you do this.
Oh, the workflow.
Yeah. I'm trying to understand that a little bit. So
yeah.
So basically, what it seems to me that, let's say you pick a basis function v1 to vn, right? And then basically you are trying to map this covariance functions here into this feature space through this expectation, which is basically just a generalization of cross covariance operator.
Right? Yeah, I mean, you can if you ignore the expectation, all we're doing is saying take the eigenproblem, t eta equals lambda eta. Pretend that eta is a superposition of the basis functions, and then the eigenproblem turns into this linear system. So it's a bog standard Galerkin expansion of an eigenproblem. The only difference here is that the inner products are computed by well, not just the inner products, but also the action of the transition operator is computed by sampling and forward simulation.
So when I look at this formulation here, especially like when you are actually writing down C hat tau, C0 inverse C hat tau. So this is actually reminded me of RKHS embedding. So basically, you can imagine that, you know, phi, such as this phi, right? They actually span some RKHS.
Yeah, I think that's maybe not so surprising, just because you're doing something very similar.
Yes. So there's this set of literature in the statistics called the embedding of conditional density or distribution. And then what happened is like you have two sets of bases. So in this case, your basis is like one as a function of x0, the other set is as a function of x tau. Mm-hmm. And then when you write down this expansion, this correlation function, in fact, it's just like a linear regression in the coordinate of this RKHS basis, which is basically C0 inverse C tau. Mm-hmm. And then basically what you're trying to do here, if I'm not wrong, is you try to represent this representation here, this C inverse, with respect to, you know, using this eigenfunction expansion. So there's something into this that you might probably want to dig this literature on this RKHS that might help you probably for, at least for a non-symmetric case.
Okay.
Because, you know, it doesn't seem like there's anything to do, right? I mean, you didn't use any basis of.
Yeah, I mean, we have to look, you know, again, there are bounds that you can get, I mean, in the reversible case, and I think in the irreversible case, if you make enough, in the
difficulty on the non-symmetric cases is you might end up going through all this complex value, and those could be hefty, right? I mean, assuming, let's just say, pure point spectrum are all there, probably, right?
Mm-hmm. Yeah, I mean, I think that the issue is that we want kind of to really say what's happening. It kind of isn't enough to just have some bounds, you know. We needed them to be precise in a certain way. For example, that the Rayleigh-Ritz bounds were not. They were not, you know, no one was thinking about varying this parameter. There was no reason to be thinking about that when they were thinking about those bounds. So
another thing that I want to ask, this is for my own intuition. Am I right if I say, okay, let's just say phi1, phi2, and phi-n, they all just linear function of x, suppose, at the moment, right? Am I
so
right
that would be like
this
that Tika scheme.
This is just a PCA?
Well, no, because, I mean, I guess it depends on what you mean by PCA, but normally I would think of PCA as, you know, x0, x0. So no time dependence.
Oh, you have a time.
I mean, I suppose people mean different things. That's what I would mean by PCA. And PCA is something I can apply to a static data set that has no meaning in time. But yeah, absolutely. There's some relationship to that. I would agree.
Because your C here, your correlation is just correlation between the data, right? But am I wrong? Like,
well, there's a time dependent, yeah, but there's this
there's a lag tau.
I mean, right. I could have a set of random variables. I estimate the covariance matrix, and then I find the eigenvectors of that covariance matrix. I would call that PCA. But in any case, this VAC method has been around for a long time. This basic workflow under a lot of different names.
Okay.
I think in the interest of time, we should probably move on. So thank you, Jonathan, again.
Thank you.
Thank you.
So